All right, so oftentimes we can draw several resonance structures from one molecule. When this is the case, we know that no one individual structure is correct, but rather a blend of all of them, or the hybrid structure, is actually the structure of the compound. However, it's typical that not all of the resonance structures will contribute equally to this hybrid, right? So the following rules, listed in order of importance, allow us to determine the most significant resonance forms for any given compound, or as we refer to it, the major resonance form, or what the major resonance contributor is. Okay? So again, these are in the order of most importance. And rule number one, the most important rule, is that the most significant resonance forms have the greatest number of filled octets for those second row elements. All right, looking at our structures here, we have two resonance structures. The one on the left has a positive charge on the carbon, and in the structure on the right, a lone pair from the oxygen has been delocalized, and the carbon now has 4 bonds. It's full octet. But since the oxygen is sharing a lone pair, it now has a positive charge on it. So which of the two resonance structures is more stable or better? It might be tempting to say the first, since the positive charge is on the less electronegative atom. But it is the second structure that is more stable, because in the second structure, all of our second row atoms have their full octet. Even though we've placed a positive charge on the electronegative oxygen, the carbon now has a full octet, and that is the most important rule. So the second structure is the major resonance contributor. Rule number 2. The structure with fewer formal charges is more significant. Now, I said this before, and I'll probably say it a million other times this semester. Nature likes neutral. The less charge we can create in a resonance structure, the more important that resonance structure is going to be. Okay, here we have 3 resonance structures drawn out. The first thing I'd like you to assess is which of these resonance structures is the worst. If you said the last one or the one most to the right, good job. Okay, this is the worst resonance structure. Why? Well, because we have a carbon central in the middle of the molecule that does not have its full octet. Again, remember, the most important rule is that resonance contributors, where every atom has their full octet, are going to be the major and the most important. In our first and our second structure, all second row elements have their full octet. So which of these two is going to be the more stable or larger contributor? Well, in my first drawing, I see that I have no charge on any atoms. In the second structure, I see that I have a nitrogen with a positive charge and a nitrogen with a negative charge. Therefore, the first structure with no charge is going to be my major resonance contributor. If the compound has an overall formal charge on it, we're going to focus only on drawing resonance forms that show the movement or delocalization of the charge. That is to say, don't make structures with any additional charges if you have a molecule that already starts with a formal charge. Rule number 3. A structure with a negative charge on the more electronegative atom will be more significant, and a structure with a positive charge on the less electronegative atom will be more significant, assuming the atoms all have their octets. Again, this is our third rule, so it's not as important as rules number 1 or rule number 2. Sometimes your resonance structure have to have charge. When this is the case, it is better to have the negative charge on the more electronegative atom and a positive charge on the less electronegative atom. So let's look at our first example. Which is the better resonance structure? The one on the left or the one on the right? Well, both structures pass rule 1, having all second row atoms with their full octet. Both structures have the same charge, one negative charge, so again, rule 2 will not apply. The first structure puts the negative charge on the oxygen, whereas the second has it on a carbon. Since oxygen is more electronegative than carbon, the first structure is best. Draw the significant resonance forms of each compound below and indicate the major resonance forms. Do this now, and we'll be going through it in class when we meet again. The resonance hybrid represents the pi bond of an allylic carbocation as being delocalized over all 3 carbon atoms. Again, this is consistent with the molecular orbital theory that we already talked about, in that the pi electrons occupying the bonding molecular orbital has no nodes and it's spread out over all 3 of the carbons. Again, we know that a hybrid, the resonance hybrid, is actually what the molecule looks like, but for reasons that will become more apparent in organic chemistry too, it is much more convenient for us to be drawing resonance structures rather than trying to draw the resonance hybrid.